Hi, in a previous video I reviewed this Mantis 3D microscope and I complained that the LED brightness wasn't adjustable on it, and for the price, well, it damn well should be. So I wanted to actually take a look at that and see if it can be modified, if it has any internal regulation circuitry or anything like that. So as it turns out, it's pretty easy to take this sucker apart. I'll switch it off here, and this top cover here just pops off, and then we've got a little diffuser thing for the LED, and let's zoom in a bit more, and on this we've got this whole assembly just comes apart here, nicely screwed in with metal threaded inserts and everything, and bingo, there's the PCB. There'll be one on each side here, and check this out. It's just got a little DC jack on there. You can just pull that off. Very nice, nicely engineered, and there's all the metal threaded inserts. It's really quite a nice design. As you can see, the LEDs are around, they're in a circular fashion, angled at a, they've engineered it at a very specific angle. So the diffuser plate sits in there like that, and it's all angled like that, and it's very beautiful. I like it. But look at this. There's no circuitry on there at all. It's just dropper resistors. That's it. So I'll measure the rest of it to make sure it just comes through from the, but I think it's just directly from the 9-volt plug pack, straight through a dropper resistor for each LED. So too easy to modify this thing, to use PWM to get the brightness adjustment, or you don't even need PWM. You can just use an LM317 linear regulator or something. And it looks like those little plastic clips there, they're like sort of those molded in type, so I don't really want to break the board out there. So I'll just measure these resistors, and can do that just fine. Bang, 82 ohms. There you go. So all they're doing is just driving this directly from the 9-volt source, I think. Okay, so what I'm going to do is I'm going to measure the to see if there's any internal circuitry in here, or whether or not the 9-volt jack just passes straight through. So I'm going to get there. I've got this plugged in here. I've got the ground here, and no, it doesn't. Hey, all right, no, I think there's the Intellect DC jack switch on there, so you've actually got to plug the thing in. So that, because I can't believe the ground's not connected, so it must be. Yep, there you go. So that ground is connected straight through to there. Now all we need to do is check the center jack on that, and the center pin here, and what do we get? Well, there's something 0.6 meg. I suspect, is there a diode in there perhaps? Let's whip that around and have a look. There we go, that looks like a diode drop, but it seems to be in the wrong direction. So I'm not sure what's going on there. There is definitely something in there though. And I cracked it open, and yeah, look what we have here. We have an LM317 in here, and also you can see the spring as well going all the way up that shaft up there. That's how it gets its nice retention system. Very nice spring. I like it, and it's attached to there. It's insulated. It's got a little sill pad washer on there, so but they're using that as a heatsink, and LM317, so I'm curious to know if that's a like a voltage regulator, or a constant current, or set up as a constant current source. Well, of course it's got to be a constant current source, because there's only 2 wires coming in and out of this in the positive supply there. So it goes through the switch, into it, and then out to the LEDs. So they've got this thing set up as a constant current source. And there you have it, folks. Now, we could have discovered all this without taking off that heat shrink, but that would have been no fun. But there you go, it's an LM317 constant current source. They've got a total of 2.5 ohms, so 1.25 volts divided by the, which is the reference voltage of the LM317, divided by the 2.5 ohms is around about 500 milliamps constant current. So we've got 24 LEDs in this thing. So assuming that they're evenly spread across all the LEDs, we should be looking at about 20.8 milliamps per LED. Let's measure that and see if we get it. Now, I've already established that these resistors are 82 ohms each, so assuming the current is shared across all of them equally, it'll be roughly something like that. Then for 20.8 milliamps per LED we're expecting, times 82 ohms, we should get about 1.7 volts across each resistor. So let's have a look. Ta-da! There you go. There you go, 1.7. So it looks like the current is pretty evenly shared across all these, not entirely spot on, but fairly well shared across all these LEDs. There you go. So these things are operating at about 20.8 milliamps per LED. So how do we go about dimming this thing? Well, obviously, because we have access to the circuitry in here now, we can add our own stuff in there. But I mean, that's quite nice. But anyone who wants to mod this thing themselves, it's not that great. They have to actually crack this thing open. So it's probably better to put something in series with this lead here, so you don't have to modify anything on your Mantis at all. So anyone should be able to do this and add the mod in or remove it as they need to. So that's a better way to do it. But this is a constant current output, so it's given us half an amp constant current. So we need a circuit in here to dim these LEDs, and well, we can do that with PWM. So let's lash up a quick little circuit and see what we can do. And there's plenty of ways to do this, but well, why not use the classic 555 timer? You can get a 555 timer to do a 0 to 100% PWM fairly easily. So what we got here is I'm going to use a 555 timer here in the PWM configuration. This is my DaveCAD drawing, PWM LED dimmer. It's a classic 555 circuit, and there's not much to it at all. We've got our input over here and our output here, and now because this is a constant, usually you don't do this with a constant current source on the input here, but it should still work, I think. So, you know, normally this is just a voltage source, and you and then you would just PWM the output, then you choose to drop a resistor based on, and we could do that if we ripped out the circuitry. We could just have the 9-volt source, and then we could calculate, well, we could actually put a voltage regulator in there, calculate what voltage is required to give the same maximum current of 20.8 milliamps per LED that we had before, or 500 milliamps, and you know, it's all too hard. So we want to leave in that constant current source. So I think this circuit will still work even though it's constant current, because we're just switching the constant current off and on instead of the voltage. Now this is the classic 555 PWM configuration. We've got an adjustment pot here which adjusts our pulse width modulation value from roughly 0 to 100%. It's not going to go over the entire range, but it's going to be pretty close. And we've got two steering diodes here, and and you know, it's quite a basic configuration. Now how this circuit works is pretty simple. When you first power it on, this capacitor is going to be a short circuit, so the trigger pin is going to set this output high here, and the output PNP transistor will be switched off because we've got a high here, we've got a high here. This transistor only switches on when this output pin goes low. So the output goes high, so the LED is starting switched off, and then we're going to charge up this capacitor through this 1K resistor here, through this diode, and through and through the pot here. So the pot is going to set our frequency as well as our PWM cycle, and then once it reaches the threshold, bingo, we're going to switch the other direction, and then our discharge pin is going to discharge that capacitor through the other diode there. Easy. Because if you remember our 555 circuit configuration, I got my 555 timer t-shirt, which you can get from my Zazzle store, by the way. I hand drew this. It's how the 555 operates, and you can see that the output here, when the output switches, it is a flip-flop. So the not Q output turns on the discharge transistor here, and that's exactly what we have in the circuit configuration. And this will come important later, I think, for a variation on this circuit. So I've got my circuit build up on the breadboard here, matches this precisely, except for one thing. The lab's a bit of a mess, and for the life of me, I couldn't find a 1N4148 diode to go in there, a 1N914 or whatever signal diode you want to use. So I had some LEDs handy just sitting here on the bench, so I used 2 LEDs instead of the 2 signal diodes there. It's going to work exactly the same, or it should, and except it's going to change, it's going to alter the frequency, but we don't really care. We just want to get this thing working. So that's the breadboard build up. I've got the BD136 PMP output power transistor here, because we're talking about 1/2 amp. So you've got to choose a transistor here which has an adequate continuous collector current in it, and this is like a 1.5 amp transistor, so it should handle that fairly decently. A 470 ohm base resistor here should give us enough current to drive that output at a 1/2 amp. Well, there's only one way to try it. Let's give it a go. And here we go. Using those values I had here, I am going to turn my pot here. I've got a 10K pot, and well, it starts down here, and you'll notice we're getting a duty cycle of a maximum 8.8%. Now this is the output on pin 3 of the 555 timer, and you'll notice that it changes PWM all the way up to 99.6% duty cycle. So that's not bad at all. Now, unfortunately, because we're using the PMP output transistor configuration here, this is actually going to be inverted. So this will be our on period. So really we're not getting close. Well, we're going to be 8 or 9% down from our 100% on period. So it's going to be on for only, you know, 91% of the time or something like that. So we're not going to get absolute maximum brightness out of this thing, but that's okay, not a problem. And I've got my I'm just powering this from the bench supply, by the way. This is not coming from the constant current source of the Mantis. That's the next step. I'm powering it from about 6 volts at the moment. I can drop it down. We're 2 volts per division there, and as you can see, I mean, the frequency is going to change. We were at what, 300 hertz before. I get down to, you know, 5 volt power supply, 5 volt supply there, and we're looking at 40 hertz or something like that. Go up to 6 volts, and it changes. You know, this thing is not stable in terms of frequency, but for our purposes, it doesn't matter. And we can go up, like if we go up to 10 volts, 12 volts, something like that, we're still going to operate over, so 99.7% to 9.2%. So our minimum or our maximum, because we're inverted, drops there at 12 volts. So anyway, this thing is going to be working at less than 9 volts, so it should work over that range quite nicely. So let's hook this up to our constant current source and see if it still works, and we can dim our LEDs. All right, first of all, let's take a baseline here. So I've got my Mantis plugged into the existing 500 milliamp source. I've got my light meter here, and I've turned off my main LED lights above me, just so it's, you know, the ambient doesn't interfere with it that much. But we just want to get a ballpark. We want to see if this circuit gives out pretty much close to the maximum and then dims. So our benchmark there is about 1630 lux. So let's plug this circuit in series with that and see what we get. And here we go. I've got it bodged into it there, so I've got it in line, and we're not quite getting the maximum there as we expected because the PWM isn't going to 100%, but maybe we have to tweak our base resistor there. So that's maximum on the pot. So if I adjust the pot, look at that. There we go. That dims quite nicely, fairly linear with the turning of the pot. So I'll show you the pot here. So, and then it switches right off at the bottom there. 177 lux. Turn it on. That's pretty nice. I like that. I think we have a winner. It doesn't quite go to the maximum lux we were getting before, so I'm going to drop that base resistor a bit. I've got 470. Let's get a, here we go, a 220. Let's give that a go. So let's go from 470 to 220 ohms and see if we can, 16. So we're getting, it's a little bit better. Bumped something here, so we're getting 1500 lux out of that thing. Let's plug the original Mantis back in. Yeah, 1600, so we're only losing 100 lux there. Not a big deal. So with our values in this circuit, we're operating from 733 hertz. It jumps up a bit, jumps all over the place as you adjust the duty cycle, down to a low of 310 hertz, so 300 hertz to 700 hertz or thereabouts with our constant current source. Not a problem. I mean, we don't particularly care about the frequency. That's much higher than any flicker that's going to be a problem, so no drama. And if you're wondering what the current output waveform looks like, the output waveform is channel 1 here, the yellow one, and the green channel 2 signal here is the pin 3 output, the Q output of our 555 timer flip-flop. So let me adjust the pulse width there, and as you can see, as I said before, it's actually inverted because we're using a PNP transistor there. So we're going from, like down under 1% there to right up to, well, close to 98%. So that's pretty good. I'm pretty happy with that. And if you're curious to see our charge and discharge waveform, i.e. pins 2 and 6, it's the bottom waveform there, and the top one is our pin 3 Q output. So you can clearly see that 0.1 microfarad cap charging up there until it hits the threshold value, and then the discharge pin kicks in, shorts to ground, and that then shorts out the cap, and bang, it goes back like that. And it oscillates. That's how the 555 works. Now we can't just leave it at that. I think this thing has got too many components, and I think we can get rid of one. So I've got another circuit here, optimized, and you'll notice that the differences between them aren't, well, there's only basically spot the difference. We've removed this 1K resistor up here, but we've swapped pins 3 and 7 like that. So now the discharge pin of the 555 timer here is turning on our PNP output transistor here, and then our Q output of our 555 timer is doing the charge and discharge, because we don't need that pull-up resistor anymore in there, because because we did need it before, because the discharge pin is an open collector output, so it doesn't have, it's not a totem pole output, so it doesn't have anything to pull it up. So we need the 1K to pull it up, but the pin 3 of the 555 timer, the Q output, is not an open collector output, so we can do away with that pull-up resistor. So we've just optimized the circuit there, and we've gotten rid of one resistor. Let's try it. So this is circuit number 2. We'll leave it here. So let's just modify that. So there's our pin 7 pull-up. So we'll get rid of that, and we'll, this base resistor here has to change. That's got to go over to pin, hang on, this is going to get messy, but, so we want our LED on pin 3. Let's just switch this thing off, shall we, for a second, and so we want that through to pin 3, our other diode through to pin 3. It's working well with these LEDs, not a problem. And we want our base resistor, the transistor, to go up to pin 7 up there. So we've gotten rid of our one resistor, we've optimized that out. Let's hook this thing back up and give it a go. Hey, it is still working. Our lux meter is switched off. Our lux meter is still reading. Oh, it's reading. What's it reading? There we go. We're up to 1600 lux. And we're going all the way down to, there you go. Not a problem. So let's take a look at those waveforms again and see what duty cycles we get. They should be near identical. All right, let's have a look at the output. We're measuring the duty cycle of the input 2 now, which is our top waveform, which is our pin 7 discharge pin. And if we adjust our PWM value, we're going down to 0.3%. Brilliant. Smoothly. Once again, the frequency does change, but whoop-de-doo. All the way up to 99.2%. Lost our trigger there a little bit, but there you go. Just get a more accurate value of the maximum. There you go. It's close to 99%. This works really quite well. I like it. 0.3% to 99, greater than 99%. Terrific. So just why were we able to swap pins 3 and 7? Well, here's the discharge pin here, and as you can see, it's the not Q output of this RS flip-flop, and the regular output is just a buffered version of the Q output. So really, these are just going to be complementary outputs. So there's no, in this particular circuit configuration, there's no problem with swapping these two pins, and by virtue of doing that, we managed to save a resistor. Beauty. So there's our final circuit. The base resistor there, around about 220 ohms. I'm using a 10K pot. I'm using LEDs in there, but we can just use regular signal diodes if you want. It's still going to work just a treat. 100N timing cap here. I'm just putting on a 10N compensation cap there. You don't necessarily have to do that. It might still work. And of course, there's a bypass cap across the rail there, but that's all there is to it. And the BD136 has plenty of grunt to drive the 500 milliamp constant current LEDs in this thing, and no, it doesn't really get warm at all, so there's no power dissipation issues there, and the whole thing works a treat over the whole duty cycle range. Very smooth, very linear really, in terms of the pot. I'm using a linear pot, by the way. I'm not using a logarithmic one, and it works just fine. So all that's left to do is build this thing up and put it in series as a permanent fix. And I'm actually using the CMOS version of the 555, the LMC 555 here, but yes, it is a genuine national semiconductor, and yes, just to add a little bit of authenticity, it is greater than 20 years old. 52nd week, 91. Nice. Now let's have a look at what it's like when it's completely assembled again. I've got both LEDs lighting down nice and evenly, and we're getting basically 4,500 lux or thereabouts, because that's a times 10 range. So, you know, 4,000, yeah, let's say 4,500 lux. Got my board built up here, ready to go. It's not heat shrunk or anything, or in a case or anything yet. So let's plug it in, and bingo, we're getting 4,300 lux. Is that maximum? Let's adjust the pot here. There we go, look at that. From 500 lux. And now for the big test, does it actually work through the viewfinder? That's maximum there. I've got constant exposure on my camera, and I'm turning the wick down, turning it down, and it's a little bit touchy at the bottom end there, but certainly we have a very nice adjustable range now. I like it. Let's put our board on a 45-degree angle there and adjust our light all the way down to pretty darn low. I like it. I mean, it's actually brighter than that in through the viewfinder. That's just my the constant exposure mode I've got on the camera there. I mean, if I turn constant exposure off, there we go, where I've turned it all the way down and the camera's still going to compensate. So I turned it all the way up, constant exposure again, and turn it all the way down. Beautiful. It's a nice smooth linear range. There's no flicker on the camera. Perfect. What a win. So that was just a quick simple hack there on some Breadboard. Not a problem. There's the output connector, which or it helps to, if it's a right angle one like that, going in, and there's the input socket and the adjust pot. Now I can mount this in some sort of case, or I'll probably put some large heat shrink over it or something like that, and I don't know, maybe cable tied up in place. I don't know. There's a few options for mounting the thing in line, but you want to sort of keep it as short as possible, I think, and just have it dangling there, really. I mean, you know, it's not often that you have to adjust this thing, so really, if it just hangs there, that's fine. So yeah, I will just heat shrink that. There we go, no problems at all. That'll give it a nice, reasonable protection, and maybe I can cable tie the thing in place or something like that, perhaps. And I'll do a second heat shrink pass on this thing so that it seals in the pot, and the pot just sort of mounts on the side there like that, and that'll hold it in place nicely, I think. So you know, it'll just dangle there. It's I can put a knob on it, but you know, frills, who cares? And it could be mounted in a nice box or something like that, but there's nothing wrong with just a bit of heat shrink like this, and maybe some hot snot as well, some hot melt glue in various places. But there you go. I think that is quite a nice little solution. I like it. And there's the finished mod. I've just got it cable tied up in there, and it just sits there really quite nice. It's all hidden out of view. I can just reach around and adjust the brightness as required. That works an absolute treat. I'm pretty darn happy with that simple hack. Yeah, could have been done better, but don't mind that at all. So there you go. If you've got a Mantis, it's well worth doing this mod to get variable brightness on your LED. It's really quite neat, and you don't have to hack the circuitry inside. It's just using the constant current source straight in. Beauty. If you want to discuss it, jump on over to the EEVblog forum. If you like the hack, please give it a big thumbs up. Catch you next time.